So let's finish this one example by finding the volume. That's where we are. We're down to actually plugging this into our definite integral and finding the volume. Now notice there is no pi here. We have not swung anything around any line. We don't have any pi r squareds going on here. So just because we're talking about finding a volume doesn't mean that we need the pi here. So try to remember that. We can see there that we found our limits of integration are going from -1 to 1. We need the area of one representational cross-section, which we found here, which was 4 times the quantity 1 minus x squared, and we are integrating with respect to x. Our thicknesses for all of our squares are with respect to x. So again, now we're just down to the calculus that we know from -1 to 1 and 1 minus x squared dx. We find our antiderivative function, pop our 4 out front, we have x minus 1/3 x cubed, and we are integrating from -1 to 1. The 4 distributes over the whole thing, so that's 1 minus 1/3 1 cubed, and then minus -1 minus 1/3 -1 cubed. All right, this is the case where our lower limit is not 0, so make sure you don't just put 0 there like we did in the last couple of examples when we were doing volumes by revolution. Again, if it's a free response question, we don't have to clean it up. So let's work a couple more examples of volumes by cross-section. Here's one where we're actually finding the volume of a solid whose bottom face or whose base is our same circle of radius 1 centered at the origin, so we know we're going from -1 to 1. But now every cross-section perpendicular to the x-axis is an isosceles triangle. And this is a concept in calculus that gets a little geometry intensive. So you have to know your geometry, and you have to know your areas of things, because again, our thicknesses come from the fact that we are perpendicular to the x-axis. These are thicknesses, so these are actual prisms, and we're adding up infinitely many of those in our definite integrals. So our thicknesses here are with respect to x, and that's where the volume comes in. So you have to know what isosceles triangle means. Well, an isosceles triangle means that the two sides of the triangle have the same measure. So in an isosceles triangle, and if we are perpendicular to the x-axis, it has to be an isosceles right triangle, just by the context that we're in. So this basically looks the same. We set our limits of integration are -1 to 1. Our top function is still that positive root. Our bottom function is still the negative root. So our length from top bounding curve to bottom bounding curve looks like this. But now our area is the area of a triangle, not the area of a square. That's 1/2 the base times the height. So that geometry looks a little bit different. But for us in an isosceles right triangle, the base and the height are equal. So it's going to look a whole lot like what we just did. It's, you know, side squared, for lack of a better description. So we're at 1/2 times 2 times the square root of the quantity 1 minus x squared. So we worked through this second example a lot quicker than we worked through the last one. So the volume is going to look like the definite integral from -1 to 1. We're adding up infinitely many isosceles right triangles with thicknesses dx. The area of a representational face looks like the square root of, sorry, I dropped my square, the square root of 1 minus x squared squared with thickness dx. So this is actually going to be the quantity 1 minus x squared dx. We find the antiderivative. That is x minus 1/3 x cubed. We're integrating from -1 to 1. And so we're going to get 1 minus 1/3 times 1 cubed, and all of that minus -1 minus 1/3 times -1 cubed. And there is the volume. Now, some of you that are strong in geometry recognize that if we have an isosceles right triangle and that the side of this triangle, or any triangle that's along in here, was the same length as the side of the squares that we did in the last problem, an isosceles right triangle set up in the plane the way we have it set up, or we could even do it like this, that's probably a better way to do it, is just going to be half of what we did before. It's just half of the previous volume that we found in the last example. And you can do it either way. You can do this as, find your area as half of a square, which is kind of sort of what we did here. Find your area as half of a square and then plug it in and find your volume. Or you can go through and do what we did, which was to find the base and the height and so forth. So one final example I want to work through. And this is where the geometry is a little bit different. And now we have a different function. We're no longer working with a region in the plane that is the circles. The base of a solid is the region between the curve y equals 2 times the square roots of sine x on the interval from 0 to pi on the x-axis. The cross-sections perpendicular to the x-axis are equilateral triangles with bases running from the x-axis to the curve. So here's our equilateral triangles. And again, the geometry of that, what you need to bring with you from geometry, is equilateral triangles have equal sides. All three sides are the same length. So whatever length this is from the curve to the x-axis is that same length and that same length. All right, and we can see that one side of our equilateral triangle is indeed just going to equal our function. So let's find all the players and then we'll find the volume and finish this example up. Well, the limits of integration are overtly given to us. It says we're along the x-axis from 0 to pi. So that part's done for us. That part's easy. The upper bounding curve is just our function given to us, f of x, or y equals 2 times the square roots of sine of x. The bottom bounding function is the x-axis, so that's actually, y equals 0, so we don't even have to show that. The length of one side is our function, so not a problem. Now we're down to the area, and we are still talking about the area of a triangle, 1/2 the base times the height of the triangle. What's different here is not our base. The 1/2 base is still the same. The base of these triangles are going to be our function. Not a problem. The kicker on this type of problem is to find the height. And in an equilateral triangle, the height that we're talking about is this distance right here. And that height is not just our function. That has to come from our work in geometry. And our work in geometry, when we are in an equilateral triangle, that turns out to be, if we break that in half, and we have our height, and we have half of the base of the equilateral triangle, and one side of the equilateral triangle, puts us in a 30, 60, 90 triangle. So we have to use those relationships that we know from geometry about a 30, 60, 90. The side opposite the smallest angle we call the short side. It will be the shortest side in that little right triangle. And the height we call the long side. Okay, and then there's the hypotenuse. And the relationship is that the short side we'll call S. We can write the long side, the distance of the height, in terms of the short side. And it turns out that the height is the square roots of 3 times the short side. It also turns out, not that we need the hypotenuse, but in a 30, 60, 90, if you'll remember, it was 2 times the short side. So when we were in a 30, 60, 90 triangle in geometry, this is a relationship that we could use. So our height is the square roots of 3 times the short side. Okay? The short side, not just the side, but the short side. Now, here's the short side. There's the short side right there. It's not our function, it's half of our function. So our height is 1/2 the square roots of 3 times our function, times 2 times the square roots of sine x. So there's the area that we're after. That's just the area of one representational equilateral triangle. And then we're going to put the dx after it, and that's going to get us our volume. So let's see if we can clean this up. That 1/2 and that 2 cancel. This 1/2 and that 2 cancels. Square roots of sine times square roots of sine is just sine. So our volume, we're integrating from 0 to pi. We have square roots of 3 times the sine of x, and then times our thickness. So even though this looks really ugly, it cleans up really nice for us to be able to find the antiderivative and therefore find the volume. So I'm going to pop my coefficient out front. What did I take the derivative of to get positive sine? That had to be negative cosine of x. And I'm going to evaluate that from 0 to pi. So this is the square roots of 3 times negative cosine of pi minus negative cosine of 0. And that square roots of 3 distributes all the way through there. So I want to make sure I keep up with that. So cosine of pi is -1. Cosine of 0 is 1. So a negative 1 is a positive 1. And then minus a -1 is a positive 1. So this is 2 times the square roots of 3 is the volume of the three-dimensional solid whose cross-sections are equilateral triangles made from the base, that is that function in the plane from x equals 0 to x equal pi. So there's our last example for volumes by cross-section. Come to class next time. We'll work several examples. You'll get much more comfortable with this concept.